So if you got no question, then this is basically what we call it autoencoder. So autoencoder is basically a nonlinear PCA, right? So it's basically starting from your data. It gets one neural network. That neural network usually takes your data from high dimensions into lower dimension, okay? So you start from this data, which is maybe, I don't know, 10,000 dimensions, for example, and then from this one, you come down into your bottleneck. The bottleneck is what we call it latent, right? The latent space. That latent space is lower in dimension. For example, this is 100 dimensions, right? And then from that latent space, you have a decoder, which is going to take you back from your latent space into your data space, right? Now, this is basically encoding-decoding architecture, and the key point here is that your input and your output dimensions are the same, right? Because you are taking your data, you want to get back to your data. This is why you call it autoencoder, right? You encode the data itself. Now, yeah, that latent representation is basically containing the principal features of your data. These are not anymore linear principal components, right? This is why I call them principal features. But at the end of the day, they have the same functionality, right? And one key point here that you see is that when you have the latent representation, if the whole compression, decompression, encoding, decoding works perfect, it means that from the latent representation, you can regenerate your data, right? So it means that if I, for example, in a thought experiment, I get one high-dimensional data, right? Say one image, which is 100 by 100, and then I can compress it into one-dimensional latent space, then there is one number only representing that, right? Now, if I tell you the number for this image is 25, then supposedly, as long as you have the decoder, you can get that 25 simply and decompress, get back to the original image itself, right? Now, it could make sense if you think tabular, like I have only 50 images, right? I match the first image by number 1, number 2, number 3, till number 50, right? If I tell you number 50, okay? Sorry, number 25, you just go in the table, look at number 25, that is the image, right? Somehow this encoder and decoder are memorizing that table, right? And then give you the right number, right indexing, right? And you only need to just pass the index now, right? Everybody's cool? This is one way of thinking about it. Now, as I told you, this is the autoencoder, and yeah, in the autoencoder, you could have any sort of module as the encoder and decoder. I mean, they do not really need to be even symmetric, right? So you can get your data and you can do super deep network to get into your latent, but maybe you decide from your latent to the output, you just use a shallower network, right? You can do that. This is not typical in most applications that we have, but maybe you deal with one application which you want to do it. Now, this architecture that I show you here is what we call it vanilla autoencoder. Why vanilla autoencoder? Because the only purpose that it has is the original purpose we had in PCA, to just compress, right? And you give you the best decompression possible. So now, one question that you might say is that, is the problem of compression is so crucial that we actually built one complete architecture for that? Well, the answer is yes and no. I mean, compression only as an application, well, it might be not crucial, which even though, I mean, it had been like, it has a very long literature, right? Even Shannon, in his first theorem, he tried to explain how perfect you can compress a source, which makes sense. I mean, when you are limited in resources, this is the most important thing for you. How much information I need to keep in order to be able to get back to what I see, right? So this problem, in principle, I mean, from the application point of view, is important. But one other thing here is that compression itself is not simply an application. It's actually a kind of outlook of a more sophisticated problem, which is representation. If you have a data, is there a very good representation for that one, which I do not understand what that is, but it's very good for the machine, right? Why this is important? Because if I have the perfect representation of everything, then I want to tell one machine, give me a CAD image, right? I represent my sentence in a very perfect way, right, with a few numbers, and I give it to the machine. Then the machine is able to start from those numbers and give me the CAD image, right? It gives me the notion of exchange between modalities, right? And this is why representation had been always a very important problem in computer science, in electrical engineering, because people always had this idea that at the end of the day, any natural thing we see, or we hear, or we sense, it's actually represented by some numerical signals, and then we don't care what those numerical signals are, right? The only thing is that those numerical signals are efficient for the machines, right? And what is the best representation? What is the best form of signaling? Yes? Somehow that is the most simple way of doing the representation. That's right, right, exactly. Yeah, that is the most simple way. Like you get really the electrical signal, you sample from it. Now you have one representation, but maybe you can process it to make it even better, right? That's a good point, right? Okay, now, yeah. Oof. So now, what if I want to do the training of autoencoders? So if I have an autoencoder and I want to train it, as I told you, you typically, in autoencoders, you don't have label, right? But the problem, the application that you have in the hand, going to help you find out what is the right label, right? If you have the very simple compression problem, you do know how to do it, right? You have your input to the encoder, you have the output to the decoder, you want to make them the same, right? So maybe we can start with this guy. So yeah, let me just skip this one because we are short a bit in time today, so I don't want to give you, I'm going to explain them on the way. So let's focus on the very first application of the autoencoder, which is compression. This means the one which we did already, right? And let's just get a bit more into it and see if I have a real neural network, encoder, decoder, how I can do the compression, okay? How can I do that? Well, I'm going to put my neural network here, right? My data is X, goes inside this neural network. It's going to give me some Z. This is the latent, right? And from that Z, I'm going to pass it through the decoder. I'm going to get X hat, right? Now, I'm going to specify my neural networks. The thing that I want at the end of the day is that my X hat be exactly the one which I decompress, be exactly the data that I had, right? Now, what about the latent space, that latent representation Z? Do you care for this application? How does it look like? Is it very important for you that, for example, Z is very dense or full of non-zero entries, or it's full of zeros? Do you care about that? No. You don't give anything about the latent right now, so the only thing important for you is that X and X hat are the same, right? So if you want to do that, what would you take as your loss function? A kind of function which is just comparing X and X hat, right? Simplest one, just you take, a kind of loss function which compares these two. Simplest one, you take X minus X hat squared, right? You just compute the squared error between these two, right? Every single pixel, you compare it to the corresponding one, how different that is, right? Simplest one, right? So you can do that. So we do know the loss. Now, if I know the loss, I'm going to send my image through this architecture. The image goes through the encoder. I start with encoder and decoder totally random, right? The image goes through encoder. It's going to give me one latent. That is not a good latent, definitely, because I have not trained the model yet, right? That latent passes through the decoder. I'm going to get something which is totally irrelevant to my original image, right? Now, I have the loss. I can compute the loss between that irrelevant output and the original input, right? So it means that I look at that output, I compare it or compute the difference to the original image that I had, right? And now that I have this one, I can compute the gradient, right? The gradient of the loss I computed with respect to output, the X hat, the irrelevant output I got, right? I can backpropagate from that one through the decoder. I get back to the gradient with respect to the latent, right? Latent itself is a function of encoder, right? So again, I keep on backpropagating till I get to the gradient with respect to everything inside that. Now that I have the gradient with respect to everybody inside the encoder and decoder, I'm going to go and update all the weights, right? Now that I updated, I again send the same image, right? This image goes, I get the latent, I get the output. The output is hopefully a bit closer to what I want, right, to the original image. I again compute the loss, backpropagate, update, right? And you keep on going till you see what you want to see at the output, right? Then you stop. Everybody's cool? Of course, if you want to do the compression of only one single image, you do it with one image, right? If you want to do it a way that is able to compress any, for example, MNIST image, you're going to give all the MNIST images, right? That makes sense. This is the classic problem we had before, right? Everybody's cool? So, that's it. For instance, if you want to do MNIST, well, you start with the MNIST. You can, I give you this example. In the tutorials, we have it. The TA will solve it for you. And then you're going to see that for the MNIST case, you actually can start from the MNIST image. Z can be as small as 2 dimensions. You just get into 2-dimensional representation. Okay? And then you can get back to your image again. It's not the perfect compression, like it's going to be a bit blurry, but at the end, you get the image itself. Very, very good. Very high quality. Like you never get 8 and you see something that is not 8. It's definitely 8, but maybe a bit blurry or something. Okay? So for the MNIST case, you can put MLP, the simplest MLP that you can think of. You can just put 4 hidden layers, and you start from 784, and you just gradually reduce it to get into 2-dimensional output, the last one, right? And for the last one, you don't need to activate. Do not activate the last layer, okay? Whatever you see that 2 outputs, that is your latent, right? Then you get that latent, and you give it to the decoder. For the decoder, you have the same thing. So you have a 4-dimensional, layer neural network. You start from 2 inputs. You gradually increase till you get to 784, right? And that guy is enough for you to compress your image. And you're going to do it perfect, as I told you, right? Now, if you want to think about how the training is going on, it goes over the 4 layers, right? It comes at the latent. That latent is directly connected to the next layer, right? And then from that layer, it again goes up, right? So you have 4 layers here, 4 layers here. That is 8 layers, right? Together. And then the thing that you do, you start your data here. It comes at the output of the last layer of your decoder. You have, again, a 784 guy, right? You compute the difference to the original MNIST image. You do it on a mini batch. You train, right? And you update the weights of all of the 8 layers, right? And gradually, you're going to get to a point where you have this middle point being the latent, and whatever MNIST image you give to it, it's going to give you roughly the same thing at the output. Yes?
It's very deep, so like you don't have like a finishing gradient because it's so deep.
For 8 layers is okay. It's not that deep. You can essentially do that. But if you want to think about like a real problem, yes. For example, UNet itself is autoencoder, right? And we always make skip connections, right? So UNet, it goes from high dimension, goes down to the latent, but in between, you always connect skip connections, right? So yes, I mean, in very realistic autoencoders, you have that. This is why you do a skip connection there. Yes?
So no matter how many layers in either like auto encoder or decoder, the only thing that is called latent variable is the thing at the bottom, right?
Latent variable, yes.
It's only the middle thing,
right? Right. That's correct, yeah. But the key point here is that when you make your encoder and decoder complex, this means that it's able to represent more and more things, right? Yeah. So for example, in this case, you have, I don't know how many MNIST images or handwritten digits you could have. I mean, the number you cannot say, right? But it's a very huge number, right? And what you do, if you think about 2-dimensional case, is that you get all of those images and you compress them in 2-dimensional points, like a circle in the 2-dimensional space, and you put points there, right? Well, theoretically, that circle has infinite number of points, right? Yeah. Correct? So it means that these points are still able to represent your data, right? The only difference here is that You need to have a super duper complicated encoder and decoder, which is able to get your data, exactly take it to the point, and then it can exactly get you back to the data, right? The more complex you make it, this kind of mapping is getting more complex and robust, right? And better matches, right? That's the point. Yeah. Yes?
How about if you have a correspondence issue? Your input is a sentence and your output is an image.
Oh, in that one, again, you don't have correspondence issue because the image is the label that you want, right? You get your whole text, you compress it, right? And then you just generate something at the output. You want it to be your image. So actually,
you have to, until the end, you know the label of the image is good or bad.
yes, but you can train it, the whole thing end to end, right? We always train everything end to end. But the thing that you are saying is not autoencoding anymore, right? Because it starts from text, I'm getting to image, right? The label is something different. The output is something different. So when you are talking about autoencoder, you always have something. You want to get back to that thing. Same thing, right? And then, yeah, that is autoencoding. Then you'd never have that problem. But the thing, I cannot think of correspondence problem here. But, I mean, that always happens when you don't know segmentation, right? The segmentation of your input, which is not the case here. Even if you have a text, you want to have that text and you get exactly back to the same text, right? And then if it learns how to do this, then gradually if you give a random text, it either get back to that text or something very close to it, right? Okay. Questions? Okay, now typical choice, in this case, you can put it like, as I told you, square norm difference, and then you just do normal back propagation and it's going to work, right? Okay, now, yeah, let me just, yes. Okay, here's one example that I have done. Like, this is a real example. I passed that 7 through the architecture, the same architecture that I showed you. I got two-dimensional representation, and if you get back, I mean, of course, you see it's a bit blurred, right? But this is still 7, right? And the key point here is that it's not going to take you exactly to the same 7 blurred. Sometimes it takes you to 7 because somehow it's understand it should put some 7 at the output, right? And somehow it gets the idea that 7 was looking like this, so I'm going to give something like that, right? Questions? Everybody's clear? So you got the idea how you can use autoencoders, right? So one thing, guys, is it okay that I keep on going? Because we're a bit short in time, so I want to finish. Thanks. So that's regarding vanilla autoencoder. Now, what we do in compression, we basically only care about getting from higher dimension to a smaller dimension latent space, right? But there are some other applications where you again might have the same autoencoding problem, but with different purposes. For instance, before I go on, I just wanted to indicate this one. Obviously, when you are doing vanilla or compression with vanilla autoencoding, your latent needs to be smaller, right? If your latent is as large as your input size, or even larger, right? Then it doesn't make to train anything, right? Correct? Because what it does is that if you encode, and then after encoding you decode, you want to get into identity transform, right? So if I get my image, I encode it, and then I decode it, I want to see the same image, right? This is the whole end-to-end process that is happening inside autoencoder. If I have the same dimensions at the encoder, at the latent, as the input dimensions, right? In that case, then, well, I can put my latent to be exactly my x. This is my encoding. I see the image, I copy it as the latent, right? And then I copy the latent as the decoded, right? The output. It's the same thing, right? As long as I have the same dimension, I don't need to do any transform, right? If I go to higher dimensions, again, you can think of it, right? I add zeros around this guy, right? I pass it to the output is going to remove those zeros, right? So it doesn't make sense to get a latent larger than your input. It's always smaller, and it's significantly smaller, right? Not just one dimension, significantly smaller, right? So I guess that is quite obvious, but just to indicate. Now, compression is the most basic application you can think of, but sometimes you have some other form of representation application. What is that one, for instance? Well, maybe you have data and you want to find out a representation for that data which is significantly sparse. What do I mean by being sparse? Say, for example, your data is 100 dimensions, and then what you want still 100 dimensional vector, but you want most of the guys to be 0. Why? Well, there is some good reasons for that, because we believe anything that we see in this nature, if we transform it into a right domain, it's going to be sparse. And you can see it in most natural things that you are dealing with, like audio signal, right? Audio signal, if you know Fourier transform, then it is superposition of multiple harmonics, right? And then if you just think about those harmonics, which are very rich in time, this is a sinusoid in time, it has values all over the time, right? But only you need to know the frequency, right? And if there are like 2 harmonics into the audio, then you basically have 2 harmonics and you can build that signal completely from scratch, right? You just generate 2 sinusoids with 2 different frequencies, you add them up, it's going to be your new audio, right? If it has 10 harmonics, just 10 different components, right? So most things that we have in the nature are sparse. Images, you can represent them by wavelet transform, and by doing that, you're going to get significantly sparse representation of your data. And there are lots of different transforms in the nature in signal processing, in computer science, that people try so hard to see the natural process. They have the feeling this is possible to represent it by something sparse, and that you just try to find out what is this sparse representation. Now, let's say that we want to do the same thing, but we don't want to do all of those analysis people used to do. We don't want to get into the Fourier theory. We don't want to get into wavelet transform. We want to do it by a neural network. We can again use the autoencoder. Yeah? How we can do it? Now, as I said, you might want to have 100-dimensional vector, which is very sparse, as the representation. You might even like to have a bit of compression, right? You would say, I had 100 dimensional data. Now I want to get from that one to 80 dimensional, a bit of compression, and that 80 dimensional should be very sparse, right? Mostly 0, right? And then I want to get back to my data, right? So you might have this one, and what should we do here? We can think again about autoencoding, right? I could say I have my data, I have this data, I want to get it into the latent. This is the representation that I'm looking for. But what should this latent have? This should be able to give me back my data, right? So this is again autoencoding. But there is one key difference here, one tiny difference. What is the difference? I don't only care about having the same output as the input. I also care about something else. What is that? If I want to have a sparse representation, what do I want? Z should be sparse as well, right? Z should have a lot of zeros, right? So it's an extra constraint that I'm putting on my problem, right? So let's see how we can do it. Well, let's say this is the architecture, so I get my data. I want to represent it with some latent. So as I told you, this latent now could be as large as my data dimension, right? If I'm only caring about the sparsity of the representation, right? Or I can make it smaller. This is typically the case. Like you have a smaller latent because you do know that even though you want a sparse representation, still you can compress. Yeah? The data that we have is significantly low dimensionals in nature. It's only our brain that can deal with the high dimensional representation of it. And we have this guy, we get into the latent. The thing that we want this latent to be sparse, and then from this guy I can get back to my data, right? How can I train this network? If I want to train this network, what should I do for the loss? Exactly. It's a regularization, right? The only thing. So the first thing that you want your data to be back, right? So x set should be same as x. This means that you're going to have this loss term, right? The second thing that you want is that you want your latent representation to be sparse, right? So this means that you want this Z guy to have a lot of zeros, right? Most of guys there are zero, right? So how you can impose this extra condition to your training? How you can do it? So I have this loss, right? If I minimize this loss, what I see at the output is same as what I send in the input, right? Now I want to have extra condition on Z. What should I do? We had it in chapter 2? No, 3? So what is it? L1 of what? That's correct. L1 of the weights. Why weights? What guy you want to be a sparse? Z, right. So L1 of Z, right? So what did we call this guy? This thing? Well, you're right. I'm going to put something proportional to the sparsity of Z. For example, L1 norm. What did we call it? It was lasso, right? But what was lasso? Lasso was the spatial form of regularization, right? So we are just regularizing our loss, right? We would say we want this loss, but we add a penalty, and that penalty is proportional to the number of non-zeros that we have inside Z, right? So when I minimize this regularized version of my loss, this is going to make my loss to be very small. At the same time, it makes the number of non-zero entries inside Z to be very small, right? And it makes Z sparse as well, right? So I can, in general, get some S of Z, some function of Z, and that function, the only thing that I need to be is that it's proportional to the number of non-zero entries inside Z, right? So as you said already, the good choice is L1 norm, right? Because we discussed about this. This is lasso. We do know that when we add this penalty, Z is going to be a sparse, right? Tibshirani could prove this, right? If you don't know this, probably you want to put L0 norm. What is L0 norm? It's just you look at your matrix, you count the number of non-zero entries, right? But that guy is not good because it's not convex. It has no derivative, right? And you cannot compute the derivative. You simply don't get gradient to train, right? So this guy is not a good thing. You never use it. This is a good thing. There are some other choices. I don't want to get into it, but if you are interested, you can take a look, right? It's not a complicated thing, even though it looks like that, right? It's just you get whatever you have as the histogram of Z, and you compare it to a Bernoulli distribution, because Bernoulli distribution itself is 0, 1, right? Yeah, you can do that, but just forget about it. If you were interested, just take a look at that. But anyways, at the end of the day, you just add one tiny extra term here, and now you're able to get your sparse representation of your data. Meaning that, with all due respect to everything in the literature, you can do whatever you get in the Fourier transform, whatever you get with wavelet transform, you can directly get it by an autoencoder, right? If you have computational power. It does not mean that those works are useless. I mean, the beauty of them is that they did it analytically, right? And they give you significant boost in terms of computation. You're spending computation here, right? But this guy is theoretically able to find those transforms as well, right? It gets your data, takes it into one sparse representation, or maybe even a better sparse representation. Who knows, right? Okay. Now, if you want to do the training, it's basically the same thing as I said before, so I'm not going to just make it super complicated anymore. So basically, you just backpropagate from here to here, and at this point, when you are backpropagating, you're going to get the gradient of the regularization term as well. That guy is going to backpropagate over encoder, and then you're going to have all the gradients to update. This means that you can train simply this architecture. That's going to be okay. Okay? Any questions? Let me just go. No question? Okay. So the first application was compression. You get data, you compress it back. You compress it and you decompress it back to your output, right? Vanilla autoencoder does that, right? If you want to have a sparsity extra, it is what we call a sparse autoencoder, and the only difference is that you add this constraint regularization on the sparsity of the latent. Other thing, which is the cool thing, and many people like it in practice, is denoising. What does it mean? It means that I have some image, old image, and this image has lots of, there are lots of points breaking there, lots of pixels missing, there are some low quality part of the image. What I want to get that guy, and take it into a very good image, right? And this is something that a few years ago, when neural networks started to do that, people started to wonder, wow, how does that do it, right? But it's not really a complicated thing. It's just a basic. I mean, autoencoder is one thing. Like, you can simply do it by autoencoding. I guess you can guess how we can do it, but let's just do it once together. It's not a complicated thing. Long story short, I have the image, right? I want to build one machine which takes low quality and it gives me high quality. I get lots of high quality images. I add noise to them, right? I ruin them. I put the ruined version in input. I make the neural network to give me the good version as the output, right? I train it on all of those data, right? Now, if you give me a new image which is already ruined, it probably can make it better, right? Everybody's cool? Yeah? So the thing that people used to do in photo taking shops old days with pencil, right? This is just being done now by the neural network, right? Okay. So basically what I want, for example, remove some background noise. Maybe I want to improve the resolution. Maybe I have a gray image. I want to make it colored. All of those things you can think of, right? Because you can get a colored image, make it gray, right? And then you just give it to the input. You train it to just give you the color version of the output, right? If you give a new gray image to it, it probably gives you a colored version, not the colored version. There's no the colored version to that one, right? Unless you had been at that point of time and have seen what are the images, right? But you can get a colored version, a meaningful color version of that. And yeah, now if you want to think about the loss that we should consider, I mean, definitely we should consider the difference between the output that we get, right, and the perfect recovery, right, the high quality image. And then as the input, we should only give the low quality image, right, which we can simply make it. So let's do it together now. This is what we call the denoising autoencoder. I want to have high quality image at the output, right? What I would do, I'm going to get my input and my original image, and I degrade it by doing something, right? It depends on the application that you have. If you want to build a machine which is able to get a blurred image and gives you back a high quality image, you blur your images, right? If you have a machine which you want to color images, you get your colored image, high quality, you reduce it into a gray one-channel image, and then you give it to your neural network, right? If you want to have some machine which is removing background noise, you get your image, your data, you add background noise, you give it as the input, and you make the output to give you the original data, right? So you can always do it. You get your original data, you degrade it, you put it at the input, and then this noisy version goes to the encoder, and then you're going to get your latent. Now at the output of the latent, you pass it through the decoder, and the output, you try to compare that decoded version to the original one that you had, right? And if you do that, then this is going to be trained to just do the denoising job that you want. So say X is the original image, X, or original data. You first degrade it to X tilde. So X tilde is the degraded version, right? This guy goes inside the input. That input is going to be encoded to the latent. Then after the latent, you're going to get the decoded version X hat. You want your X hat to be exactly X. And if you need some extra condition on Z, like for example, in addition to doing the denoising, you want it to be sparse, you can add that constraint on your latent as well, right? So at the end of the day, you have something like this. If you don't have any sparsity or any other form of constraint, you can drop this regularization term here. And the key point here is that you compare your output with the original image that you had, right? And again, you can train this, right? Now, this is a kind of nice experiment if you wanted to just challenge yourself, right? At least for MNIST, that is super duper simple. With the same architecture I told you, you can do it. I mean, probably you need a bit of higher dimension for latent because you're removing some noise, but you can simply do it. But you can even challenge yourself a bit more, like realistic images. It's going to take a bit of time to get trained, but then you can do it very perfectly. Okay? Questions? Yes?
Can we train the whole thing and then use the latent to train another
Yes, you can do that, right? Yeah, I mean, sometimes you do it. But you need to know that the representation is actually a good thing for your next architecture that you are connecting it. Actually, we do a bit of this right now when we want to generate, but not with the encoder, with the decoder. Yeah, okay. We don't have label, we build label, right? Because but nobody gave you a kind of bad image, right? They just give you a bunch of images until it told you, can you build one machine, which remove noise, right? So there's no label here, it's still, right? But you can do it. You just get your data. I mean, your data is the label now, right? And then you just build the input from it, right? Yeah. Questions? No question? Okay, summary, vanilla one is mainly doing the compression. You have the sparse one, which can give you a specific form of representation if you really need to do that. And you have the denoising one, which is the cool guy. You can just simply remove noise from your data if you wish, right? Now, these guys were